Okay, so welcome back to 10.1 part 2. We just finished working with these the square root of something squared, and we noted that they kind of undo each other, and then you're left over with the insides here. But we have to be careful and include an absolute value unless told otherwise. And it turns out that later on you're going to, they'll just say assume that whatever's in there is positive. Um, anyways, what do we got? Cube roots and cube root functions. So it's the same plan as before. As the square roots, we want to go through and kind of analyze these things. Cube roots, cube root functions. Okay. So this time you're thinking of undoing the cubing process, right? So cubing, maybe we have something like 3 cubed, and that'll equal 27. I'll put some lights on here. Hopefully you can see it. And then maybe something like 5 cubed is 125. We want to go in the opposite direction. Fortunately for us, there won't be this issue with all that absolute value nonsense. Whenever you have an odd root, so cube, we think 3. Whenever you have some sort of oddness, we don't have to worry about the absolute value. So we note that if you had negative 3 cubed, you're not going to end up with 27, right? A negative times a negative. So we would have negative 3 times negative 3 times negative 3. And a negative times a negative here will give you positive 9, and then times negative 3. And then 9 times negative 3 is negative 27. So we're in the clear, right? We're going to get different answers this time, and it's nice in that way. You don't have to worry about all of this weird business with the absolute values. Okay. So that's the cubing process, and of course we are interested then in the reversal of that process, the cube root. The camera is kind of out of whack here. Okay, I guess that's good enough. So the cube root, before 3 cubed was 27, so therefore the cube root, you're going to know it's a cube root because there will be a little number there. Here are 3 for cube. Actually, there's always a number there, even if you're dealing with square roots. We don't explicitly write it, but it's kind of assumed that there's a little 2 there. Okay. So anyways, that's 5. We don't care about the square roots now, but the cube root will undo the cube. So the cube root of 125, then from our previous work on the last page is just 5. So the book is going to drag you through some exercises on this phenomena. The cube root of negative 64. So what times what is negative 6? What times what times what is negative 64? Negative 4. So another difference here is you could take the cube root of a negative and not have to worry about it not being real. Okay, so these guys will work in this setting. Let's look at one more cube root of a fraction here. Negative 8 over 125. If you cube a negative, you're going to get a negative result. Okay. And then what times what times what is 8? That's 2. What times what times what is 125? That's 5. And there's our answer. Okay. We could also graph these, just like we graph the square root function. The graph of these things. This time the domain, the things that you're allowed to put into the cube root function are the real numbers. Okay, so we don't really have to worry about that negative phenomena, which we had to worry about with the square root. mic over here closer to me. Oh, I'm not on the board. Yeah, so here's what it looks like. F of x equals cube root of x. And the numbers that you could put into the cube root, the x values, are from negative infinity to infinity. Okay? We can plot this guy doing a t-table. You want to pick x values that are perfect cubes. You don't want anything too big, so like -8, cube root of that's -2. Maybe we should have included another one, right? -1, the cube root of that is -1, 0, the cube root of 0 is 0, 1, the cube root of 1 is 1, 8, cube root of 8 is 2. Okay. So we need 8 tick marks on the old X bar there. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Then we want to go up to 2 in either direction. Okay, so at -8, it's at -2, sorry. At -1, it's at 1. 0, it's a 0. 1, it's 1. And then at 8, it's 2. It goes like this. Oops. You shouldn't dip down like that. You should just keep going straight. Look in the book for a good picture, or look online for a good picture. That's not a very good picture, but that's it. That's the idea. It's not exactly like the last one I was showing. If you tilt it this way, it kind of looks like a parabola. And this is kind of the same deal. It's not really the same shape as a parabola this time. It's a sort of a twist. It's comes down, and if you flip this over the y-axis, it would actually be y equals x cubed. Again, the cube root and the cube function are inverses. Okay, so part G, then again, we want to worry about simplifying them when we see them together. So what did I say? What is basically the cube root of something cubed, right? And what does that look like? I'm going to take the cube root of something cubed, and the cube root and the cube will just annihilate each other. You don't have to worry about absolute values or any of that business. You just end up with the x. The cube root and the cube eat each other, so to speak. So let's look at 82. We have the cube root of -125 x cubed. So if you want, you can rewrite this as -5x and then cubed. So I want the cube root of that. If you take the cube of something cubed, you're just left with the something. Okay? You're just left sort of with the guts, and that's exactly what we get. Okay? You don't have to worry about the absolute values this time. Okay. In general, we'll talk about even or odd roots, and the even roots are always going to have this issue with the absolute values. The odd roots are always going to be fine. Okay, so also the even roots will always have the issue of the non-real solution. Right, you can't put a negative inside of an even root. And again, what do I mean by even and odds? This guy's an odd root because its root is 3. It's a third root. 3 is odd. Okay. So what are even numbers? 2, 4, 6, 8, 10, 12. Those are the evens. This one's odd. Okay. So in general, we can look at these other guys, these other kinds of roots. We can say, all right, we're going to divvy them up into 2 types, even and odd. And in general, we call them nth roots. So 5th roots, 6th roots, 7th roots, 8th roots, 9th roots. In the beginning, we'll just work with evaluating them, or the arithmetical versions. So you're just working with numbers in the beginning. You don't have to worry about variables. So here I got the 5th root of 1. Okay, so what times what times what times what times what is equal to the 5th, is equal to 1, sorry. 1, of course. Here we have the 4th root of 81. So what times what times what times what is 81? That's probably 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. 68, we have the 7th root of -1. It's an odd root, so we can take the odd root of a negative, and we're left with a negative. And if you work it out, yes, -1 times -1 times -1 times -1 times -1 times -1 times -1 is -1, okay? So it does work. If you don't believe me, try it. 66, the 4th root of -81. So certainly 81 is just 3 times 3 times 3 times 3. But because we have an even root here, we can't do this in the real numbers. Okay, so we'll say it's not real. And of course, if it's positive, then you're okay. So over here, we had the same scenario root, even root, but positive on the inside, so we could do it. But here it's even root, negative on the inside, can't do it. And down here, of course, odd root, negative on inside, you can do it. Right? Okay, so even root of negative is never real. So even root of a negative, not real. Odd root, though, is okay. And you'll end up with always with a negative. So the odd root of a negative will be a negative real. Okay. Okay. So this time, then the simplifying. What happens if I take the nth root of something raised to the nth power? Do they just cancel each other out? And yeah, if the nth root is odd, right? So if n is even, and you take the nth root of something raised to the nth power, you got to use the freaking absolute values symbol. Right? If n is odd, then the nth root of something raised to the nth power is just going to give you that something back. The root and the power will cancel each other out, and you'll start back you'll end where you started, basically, is what I'm trying to say. Okay, so let's chug through a couple of those. Here we have the 6th root of y to the 6th. Okay, so these are even. So you're left with y, but you have to slap on some absolute values for safety purposes. Okay. Let's try 84. That was 80. Cube root of -6 cubed. Okay. And here, no problem, right? You just write -6. 86. Here we have the 6th root of -6 raised to the 6th. Okay, so certainly the roots will go away, you're left with -6, but because it's an even power, you have to include the absolute values. Of course, the absolute value of -6 is +6. Okay, there's some extra problems in there that may be a little bit difficult and challenging. Let's look at one of those extra. Find the domain. And let's look at the function you're dealing with, 97. F of x is the square root of x minus 1 all over the square root of 3 minus x. Okay. So there's two issues here. you can't have zeros in the denominator. All right, so first off, I need to make sure when I build my domain, I don't include anything that would cause a 0 in the denominator. So I need to make sure that 3 minus x is not equal to 0. Okay, so how do I figure that out? I'm going to set this equal to 0 and then square both sides. Okay. You don't have to worry about absolute values here. It's only when you take the square root of something squared that you worry about that. Here, it's not the same deal. The square root and the square will go away. And we see if we add x to both sides, 3 equals x, or in other words, x equals 3, right? So we can't allow x to be 3, or otherwise there would be division by 0. We can never divide anything by 0. So for example, 3 over 0, that's bad news. It's undefined in math. Okay, what else then? We need to make sure that the stuff inside of the radical is positive. In other words, I need to make sure that x minus 1 is greater than or equal to 0. And I need to make sure 3 minus x is greater than or equal to 0. Okay? So over here, x greater than or equal to 1. And over here, negative x greater than or equal to negative 3, multiplied by negative 1. X needs to be less than or equal to 3. Okay? So I need both of these to be true. So I go to my number line and find where those intervals overlap. Okay? So I need this to be true and this to be true. So here's 1, here's 3. I need everything greater than 3, or sorry, greater than 1. There's 3. So I need all of this stuff. And I need everything less than or equal to 3. So in this direction. So the overlap turns out to be this interval right here, right? There's one other issue involved. We can't have x equaling 3, so I have to kind of throw out the number 3. It's just the interval from 1 to 3. Okay, so the domain here, I go from 1 to 3, and don't include 3. So put a parentheses there to remind yourself of that fact. Okay, so these domain problems can get pretty difficult. It's just not a matter of one thing. It's you have these functions that are the result of adding, subtracting, multiplying, and dividing other functions. And then to figure out their domain, you kind of look for the overlap of acceptable values. Okay? And that's what we ended up with here. Okay, so that's the end of that.